Okay, so for folks who are joining or checking this out later, we are in week 4 now. We have an exam this week, and so the new material actually isn't that significant. It's a good week to get caught up if there's older web assigned problems that you need to finish up still. Um, Today, I'm going to take a look at some of the web assigned problems involving exponents and logarithms. I'll do a quick summary of the new material. It's really straightforward. If you're solid with derivative rules from previous chapters, really the only thing that we're adding this week is a couple more functions whose derivatives we're now able to take. So here's the quick summary. We're adding really 2 functions. We're adding the derivative of the exponential function, so d dx of e to the x. Okay, now you might be a little bit worried, like e to the x, it's an exponential function. Just to be clear, e is a irrational number. It's about 2.7, a little bit more than that. Expressed as a decimal, it goes on forever. Has some really interesting properties. If you imagine all the different exponential functions, so like 2 to the x, 10 to the x, 100 to the x, 0.01 to the x, all of those exponential graphs have similar shapes. Like all the exponential growth functions look like this, right? And they get steeper as time goes on, or as we go farther to the right. Exponential decay functions are just like a mirror image of that, basically. And the steepness of that curve, how fast it grows, is proportional to the base of the exponent. So, for example, y equals 10 to the x grows faster than y equals 9 to the x. Y equals e to the x has a really interesting property. It grows at exactly a speed so that the derivative of the function is itself at any moment. So the slope of the tangent line to the curve is exactly the same as the y value of that point. So most students find this to be a relief. It's like, okay, just when we started getting comfortable with derivatives, I add some more functions like exponentials and logarithms, and we get a little bit panicked because we don't remember a lot about exponential logarithmic functions. But here's some good news. The derivative of e to the x is e to the x. Here's some more good news. The natural logarithmic function, so ln x. And just to be clear here, when we write ln x, we mean log base e of x. So logarithm base e of x. So its derivative is also pretty straightforward. It's just 1 over x. And so these are 2 new derivatives that are introduced in this chapter. And you do need to know a chain rule version of each of one of these as well. They're not even really separate formulas. The chain rules sort of give us a general way of taking exponential logarithmic functions or any composition of functions here and finding their derivatives. But I'm going to still add them here. I'm just going to put them right on this whiteboard here. So d dx of e to the u. Now, notice what I'm doing here. I'm using u as a placeholder for some function involving x's. So it could be like x squared plus 2, or it could be e to the x. We could have e to the x, or e to the ln x. Some other function is u here. Okay, so what does the chain rule say? Chain rule says take the derivative of the outside function. So take f prime of g of x, which would just be e to the u, right? Because the derivative of e to something is e to something. And then chain rule says multiply by the derivative of the inside function. So multiply by the derivative of u. And so this is, I don't know if I'd call it a shortcut or a summary. This is how the chain rule is applied to the exponential function. You don't necessarily need this as a separate formula. Similarly, for the natural logarithmic function, if we take d dx, not of the natural log of x, but of natural log u, so we'll take the derivative of the outside function, so natural log. So that gives us our 1 over u. And then the derivative of the inside function we'll multiply by, so multiply by u prime, just like we did up here. And sometimes you'll see this written as u prime over u, right? That's just an equivalent fraction form of 1 over u times u prime. So this is like the big new idea, and I think like 5.4 introduces derivatives of exponential functions. 5.5, if I remember right, introduces logarithmic functions. And there's one more topic called logarithmic differentiation I don't really want to get into today that we can use for a variety of functions as well. Maybe I might get a chance to do that a little bit later on. I did want to go and take a look at some of the problems from these sections here. So if you bear with me, I'm going to just share my screen from WebAssign. Okay, so here's WebAssign 5.5. 14 questions here. I'm going to pick a couple to do. and then call that good from this section. So maybe I'll do problem 5. I'll talk about it and copy it down and then switch back to the whiteboard here. So problem 5, I have f of x equals 8x squared times the natural log of 7x. You know, one thing I know, having taught this course before, is sometimes we have students who are really comfortable actually with limits and derivatives, but the logarithms part, it's just something that didn't stick with them in previous courses. So it's okay. Like if you need to go back and do some review on properties of logarithms at the beginning of the book, that's fine. I found that half or more of the students need to do that. So don't feel bad if you don't remember a whole lot about logarithms. I do have a couple comments just on the structure of this problem here. So let's see, what do they want? They want us to take f prime of x. So back to the whiteboard here. We're gonna find f prime of x. Okay, first important thing to realize is that natural log is a function. It's not a variable. This is not ln times 7x. This is a function, just like a sine wave. A sine function takes an angle as an input and it outputs a ratio of side. The natural log function takes as input 7x and is going to output something else. So that means we can't like divide out the 7. We can't split this into ln times 7x. It's not ln 7 times ln x. It's just one single unit here, natural log of 7x. And so the structure that I see in this problem before I do any calculus is that this is set up, f of x is set up as a product, right? There's one thing, I don't know, maybe I'll call that A. And then here's this other thing, B. All right, I'm just adding this commentary myself. I'm adding structure here to keep myself organized in the problem. Once I recognize it's a product, I know that my derivative f prime of x is going to be A times B prime plus B times A prime. And then all I need to do now to finish the problem is find that A prime and that B prime and plug them in the appropriate places. Okay, well, if I'm calling 8x squared A, then A prime is pretty easy. A prime would just be 16x. And B prime, okay, so B is natural log of 7x. So just looking back up here, I don't have natural log of x, I have natural log of u, where u is 7x. So I'm going to use my derivative right here, letting u be 7x. Sorry, bring it down so you can see it. And so then B prime would be 1 over u, so 1 over 7x times the derivative of 7x, so times 7. This is interesting. You'll see this pattern pop up if you do a bunch of problems like this. And so we have a 7 over 7x. We don't have to, but if we wanted to cancel that, that just cancels the 1 over x. It's interesting. It turns out it doesn't matter if you have natural log of 7x, natural log of 100x, natural log of negative 2x. The derivative always ends up just being 1 over x in this case. All right, so now I have my 4 ingredients. I have A, I have B, I have A prime, I have B prime. To get my answer for f prime of x, I just need to put them in the right places. So I have my A, so 8x squared times B prime, which is 1 over x. And then I'm going to add that to B, which is natural log of 7x. We're going to multiply that by A prime, which is 16x. Whoops, we're running out of room there. And this is fine. You can leave it just this way. I don't need to like cancel an x or anything like that. I do want to be really clear when I write that natural log. I'm taking natural log of 7x, and I'm not taking like natural log of 7x times 16x here. And so I'm done with my problem here. All right, let me go back to screen share here. We'll take a look at least one other problem. So that was a problem. If you think about all the pieces to that last problem, we used derivatives of logarithmic functions, we used the product rule, and we used the chain rule to solve that problem. I think actually here's what I'm going to do. I'm going to do problem 11. I'm going to copy it down and talk a little bit about logarithmic differentiation. That was that topic I was like, well, I don't know if we'll get to it. It's probably worth our time. Logarithmic differentiation is actually a really powerful tool for making complicated derivatives into actually pretty straightforward ones. So let me just copy down this function I have here in problem 11. I have y equals the square root of 7 plus 5x squared divided by the cube root of x squared plus 1. Okay, so let's take a look at that. So that's not the simplest looking function here. And regardless if we use logarithmic differentiation or not, hopefully by this point in the course, you know that anytime we have roots, first thing we're going to do is rewrite them as exponents. So I have 7 plus 5 x squared to the 1/2 power. We're going to divide that by x squared plus 1 to the 1/3 power. Now, I'm not super excited about this expression, and here's why. If I just started trying to take y prime, well, first of all, I have a quotient, right? So I'd have to use quotient rule, where my lower function is x squared plus 1 to the 1/3, and my upper function is 7 plus 5x squared to the 1/2. To find that d low and d high, I would then have to use chain rule on each one of these. So I'm looking at a problem that has quotient rule and then chain rule within the quotient rule in both the numerator and the denominator. It's going to be a mess. So I want to show you how to do this problem using logarithmic differentiation. And it ties back to a couple things in the past. One is implicit differentiation. You remember in implicit differentiation, we took the derivative of both sides of the equation and then rearranged it until it gave us what we wanted. So that's one part of what we use for logarithmic differentiation. The other part that we use are some properties of logs, and I'm just going to write them here on the right-hand side of the whiteboard. These properties of logs can be proven. They're all derived from properties that we know about exponents, and here are the ones that are really helpful. If we're taking, I'm going to write them as natural logs, but they're true for all logarithms of any base. In calculus, we tend to use base e pretty much all the time. We use natural logs because of how nicely they behave. So if we're going to take the natural log of two things multiplied together, so I'm going to write it ab, so natural log of a times b, we are allowed to take the natural log of the first thing and add it to the natural log of the second thing, so natural log a plus natural log b. I won't go off on too far of a tangent here, but the reason that logarithms were originally developed were as a practical tool for doing complicated multiplication problems. If you imagine 150 years ago, working in an architectural firm or building ships or something where there's very complex calculations that are needed, there would be a whole team of mathematicians whose job it was just to do these problems. Now, if you've ever done multiplication by hand, you can imagine doing a 9-digit number by a 9-digit number by hand without making a mistake. So it's time consuming, and there's a decent chance that you're going to make a mistake. Logarithms were developed so that we could leverage properties like this. Instead of multiplying two numbers together, we could take the log of that product, add them, and basically reverse the process afterwards. It doesn't really matter for what we're doing today, but it is an interesting story in math where something started as a practical tool and then became more of a theoretical tool for studying functions a little bit later on. So here's three properties. We might call this a product rule because we're taking the natural log of a product. We also have a quotient rule for logs. So if we're taking the natural log of a quotient, probably unsurprisingly, it's very similar, except we're going to subtract natural log a minus natural log b. And then finally, if we're taking the natural log of some exponential expression, so a raised to the b power, that b can actually just come out in front. So b times natural log of a. The proofs of these things are pretty interesting, but I'll let you explore that on your own. If you're interested, if you're not, you can just trust me that these things work as an extension of properties of exponents that we already know. Okay, so logarithmic differentiation, the idea is we're going to take the log of both sides of our equation, use these properties of logs, and then we will be able to rearrange it as we see fit. You know, I'm going to add one more thing here. I mentioned it when I first introduced the exponents and logs that they're inverse operations, or they're inverse functions. So inverse functions, if you apply one and then apply the other, you're back where you started. So one thing that we might also use is the following: e raised to the ln x and the natural log of e to the x. These are both equal to x. So another way to think of this is if we started with x, we plugged that into a natural log function, something came out, then we plug that in to the power of e, then we would be back where we started with whatever that value of x was. And vice versa, if we took some number as the exponent for e and then took its natural log, we'd be back where we started. So these properties together will help us out here. So I'm going to ignore this part for now, like this middle part. I'm just going to focus on the equation y equals the equation with its fractional powers. So I'm going to do now, if they're equal, if y is equal to this lovely fraction here, well, then their natural logs must also be equal. So it must be true that natural log of y is equal to natural log of this fantastic thing. I'll copy over now. 7 plus 5x squared to the 1/2 divided by x squared plus 1 to the 1/3. Okay. Now this is where it gets interesting because what we have on the right-hand side is the natural log of a quotient. And unlike the quotient rule of derivatives, the quotient rule of logarithms is actually pretty straightforward. Quotient rule of logarithms says we can rewrite this fraction as just 2 logs. Natural log of 7 plus 5x squared raised to the 1/2 power minus natural log of x squared plus 1 to the 1/3 power. This is still equal to ln y. All right, so I just applied the second rule of logarithms. Now I no longer have a quotient, which is great, right? Who wants quotients? Who wants to take quotient rule for derivatives? We don't have to. Okay, well, let's see what else we can do. I'm noticing now that I'm actually still, and actually my parentheses aren't fantastic here. Should probably have something like that just to indicate that the 1/3 is power and the 1/2 power are still parts inside that logarithm. Well, now I can use this third property, this exponent rule for logarithms, that says we can take our powers and just write them out in front as a coefficient. So now we have natural log y equals 1/2 times the natural log of 7 plus 5x squared minus 1/3 times the natural log of x squared plus 1. And while it's true that this is getting a little bit longer, the good news for us is that these derivatives are now very easy to take. We no longer have chain rule, or we only have one level of chain rule, but previously we'd have chain rule within quotient rule. So I haven't done any calculus yet, just done some college algebra properties of logarithms. Now I'm going to take ddx of both sides. So ddx of the left-hand side, ddx of the right-hand side. Hopefully you'll forgive me for just writing ddx and ddx, so I don't have to make a whole new line. Okay, so ddx of natural log y, here's where the implicit differentiation comes in. The derivative of natural log y, that's the same as the derivative of natural log u. So it's 1 over y times y prime. Okay, now on the right-hand side, taking ddx of each one of these things here. So I'll have 1/2, and now this is like an ln situation. It's a chain rule situation. I'm not just taking the derivative of natural log x, I'm taking the derivative of natural log 7 plus 5x squared. So what do we get? We get 1 over u, so 1 over 7 plus 5x squared, and we multiply by the derivative of the inside function. So multiply that by 10x. That's the derivative of 7 plus 5x squared. And then for my other term here, for my minus 1/3, I have minus 1/3. And again, this is that ln u that we're taking the derivative of. So 1 over u, 1 over x squared plus 1, times the derivative of u, so times 2x. And we are almost done. What I don't want to do now, I don't really want to like multiply these fractions out. I'll just like leave them the way they are, and they're kind of a mess. If you notice what this is all equal to, it's not equal to y prime. It's equal to 1 over y times y prime, and we've been asked to find y prime. So the last step for us is just going to be to multiply both sides by y. And I need to multiply all of both sides by y. So really what I'm doing here is I'm taking this whole thing in parentheses, multiplying by y, multiplying by y. I'm going to get cancellation here. And this is almost my answer. I'm in really good shape, except the original problem didn't have any y's. When you do implicit differentiation, you're given a relation that has x's and y's together. It's okay for your derivative to have x's and y's together. But since our original function was given explicitly, y is an explicit function of x, I'm going to take one more step to substitute back my original function for y to finish the problem here. So y prime equals this fantastic expression here. So 1/2 times 1 over 7 plus 5x squared times 10x minus 1/3 times 1 over x squared plus 1 times 2x. So last step, instead of writing this as the variable y, I'm going to go back to the beginning and take my expression for y and use that instead. So here I have 7 plus 5x squared to the 1/2 over x squared plus 1 to the 1/3. So it's not an easy problem, but it's still a lot faster and easier than using quotient rule and then chain rule and then chain rule again. I'm not going to take the time right now to plug this in to WebAssign. I do know that these problems can sometimes be frustrating because you make a small mistake somewhere and it passes all the way through to the end. So logarithmic differentiation, it's useful for problems like this. We have like quotient rule, product rule, chain rule, a bunch of exponents. Logarithmic differentiation might make the problem easier. And I want to show you one more problem, and then I'll quit. Or one more type of function family where you have to use logarithmic differentiation. So here's an interesting function, y equals x to the x. And so this is neither a polynomial, like y equals x to the 10th, that's a polynomial. And y equals 10 to the x, that's an exponential function. Got polynomials and exponential functions. We can work with both of these if we need to. This is neither, and it's a function that grows really fast. If you imagine what's happening here as we go from left to right, the base of the exponent is getting bigger and the exponent is getting bigger at the same time. So this is a function that grows really quickly. But we don't really have a differentiation rule for how to deal with this. Like, do we try and get it into like e to the x form? Do we try and get it into a polynomial form? Well, what we can do is take the natural log of both sides. We can use logarithmic differentiation. So ln y equals ln of x to the x. And now we have properties of logs that says we can take that exponent and just plop it out in front there. So we have natural log y equals x times ln x. And now I can differentiate. So I'll take d dx of both sides. On the left-hand side, I have y prime. 1 over y times y prime. Equals, okay, well on the right-hand side, I'm going to have to use product rule. So I'll take my first function x times the derivative of the second. Derivative of ln x is 1 over x. And then add that to let's see, do I have that right? First times the derivative of the second plus the second times the derivative of the first. So ln x times 1. And I actually am going to do a little bit of simplifying here because I have an x times 1 over x. So really, so far I just have 1 plus ln x equals y prime times 1 over y. And so if I multiply both sides by y, I can now substitute for y to finish the problem. So what I did here, multiply both sides by y to cancel the 1 over y. And now I'm going to trade out y for x to the x. And so our derivative then is x to the x times 1 plus ln x. So there are a few types of functions for which we would have to use logarithmic differentiation. There's always a telltale sign. It's that we have exponent, or we have variables in the base and the exponent. So like if you had, I don't know, if you had like ln x raised to the power of x, like there's another function that we couldn't take its derivative without using logarithmic differentiation. Or x to the x squared minus 1, something like that, or x to the natural log of x squared. We have to use logarithmic differentiation. And again, in a nutshell, logarithmic differentiation, what we do, we take the log of both sides, we use some properties of logarithms that are up here. I also believe these are introduced at the beginning of chapter 5. So if these aren't super familiar, you should be able to find them in chapter 5. Just have them as a reference as you work. And then we differentiate. So we took the log of both sides, we used properties of logs to make things simpler. We used implicit differentiation on both sides, and then finally we solved for y prime. And the important thing, the place where I see a lot of people lose like 1 point is they get to here, they get to this step, and they forget to back substitute for y. They forget to trade out y for x to the x or whatever the function may be.